Have you ever tried to organize something truly complex, like maybe a big group project, where pieces of information just kept arriving out of order?
Oh, definitely. Or even just sorting digital photos, right? Where the timestamps seem all over the place.
Exactly. It's like trying to solve a puzzle when some of the pieces show up really late. And that's actually a huge challenge in the world of high-speed data.
It really is a fundamental one.
So today, we're taking a deep dive into something called watermarking techniques for data streaming platforms.
Sounds technical, I know.
It does, but trust us, it's a foundational concept. It quietly powers so many of the real-time experiences you interact with every single day, often completely behind the scenes.
Absolutely. And this deep dive, it's based on a request for information document, an RFI, that was comparing these exact techniques across the leading platforms out there.
Right. It was put together to help a big organization figure out the best tech for handling just massive amounts of real-time data. Data that, like we said, might arrive a bit, well, behind schedule.
Yeah, fashionably late data, you could say.
So our mission for you today is to cut through that complexity. We want to uncover what watermarking actually is, why it's so crucial for accurate real-time data, and how the different major platforms tackle this challenge.
And by the end, you should have a really clear understanding of this vital piece of the whole data streaming puzzle. You know, the piece that brings order to potential chaos.
Okay, so let's paint a picture. Imagine data flowing like a river, a really fast-moving one. In these real-time data streams, events are constantly coming in, things like sensor readings, or maybe online purchases, system logs.
All sorts of things happening all the time.
But here's the kicker, the tricky part.
Mhm.
They don't always arrive in the exact order they actually happen.
Right. And sometimes they can be significantly delayed. Network hiccups, device issues, you name it.
And this late arriving data,
Yeah.
that's the technical term, it poses a really significant challenge, especially for something called window-based aggregations.
Okay, let's break that down. Think about wanting to accurately count, say, how many online purchases happen in a specific 5-minute window.
Or maybe the average temperature reading from a sensor over a 10-minute period.
Exactly. If data that belongs in that 5 or 10-minute window arrives after you've already calculated your result, well, your aggregation can be wildly inaccurate.
You end up with this constantly shifting, unreliable picture. Not ideal.
Not ideal at all if you need to make decisions based on that data.
And this is precisely where watermarking steps in. It's absolutely essential. It gives the system a mechanism, a way to confidently say, okay, look, I'm reasonably sure I've seen all the data up to this point in time.
And I can now finalize my calculations for that period.
It's the linchpin, really. It allows these real-time systems to make confident, final decisions about past events.
Exactly right. Watermarking allows the system to estimate the progress of event time within the stream. And event time just means when something actually happened out there in the real world.
Not just when your computer system received the data point.
Correct. The watermark defines a specific point in event time. The system basically assumes, or makes an educated guess, that all data prior to this watermark time has now arrived.
So once that watermark passes a certain point,
Window aggregation calculations for periods before that watermark can be performed reliably. It ensures accuracy without, waiting forever for every single possible late piece of data.
it's a trade-off then.
It is. It balances that need for real-time accuracy with practical system performance. You can't wait indefinitely.
So what happens if data arrives really late, like after the watermark is passed?
Well, the system, based on its configuration, might choose to ignore that data,
Sure.
to drop it, because it falls outside the processing window defined by the watermark at that point.
Okay. To make this really concrete, let's trace an example. This comes straight from the source material we looked at. Imagine a system where the watermark is set to tolerate, say, a 5-minute delay.
Okay, so let's say it's 8:15 a.m. in processing time. That's the system clock. And the latest event the system has processed so far actually happened. Its event time was 8:13 a.m.
Still with you.
Now, here's how the watermark helps decide when a calculation window is complete. You apply that 5-minute watermark duration. So 8:13 a.m. minus 5 minutes gives you 8:08 a.m.
Got it.
This means the system can now confidently finalize all the calculations, all the aggregations for any time window that ended before 8:08 a.m.
So for instance, the window that ran from 8:00 a.m. to 8:05 a.m.
That one's now considered complete, done. Its aggregated results can be reliably released downstream.
Wow. Okay. That seemingly small detail, that calculation, it ensures the integrity of your aggregated data. It's the moment the system says, Right. This time window is closed, the results are final.
Precisely. It brings certainty to the stream.
Okay, let's break this down even further then. We understand what watermarking does, and we definitely see why it's vital for getting accurate results in real time. But how do the big players, the leading streaming data platforms, actually implement this?
Ah, yes. The RFI document we reviewed dives into 4 major ones.
And what's interesting is,
Well, what's intriguing is that while they're all aiming to solve the same fundamental problem, handling late data, their approaches are quite different. They vary significantly in things like flexibility, how easy they are to use, the latency you can expect, and, the best scenarios for each.
all right, let's compare them. First
Okay.
up, PySpark structured streaming. What's the story there?
PySpark is often highlighted for its relative ease of implementation. It offers native declarative watermarking. That means you use a pretty simple API call, like with Watermark.
So simpler for developers?
Generally, yes. It's strong for handling that late data, with built-in policies for deciding whether to drop or accept late events. Now, a key thing about PySpark structured streaming is that it typically uses micro-batching.
Microbatching, you mentioned that. So it's not truly real-time record by record.
Not usually by default, no. It processes data in small chunks, small batches, maybe every few seconds, or configurable, so its real-time processing latency is tied to those batch intervals.
Okay. And the best use case?
Our source material suggests it's ideal for large-scale streams where you can tolerate some latency due to batching, and especially where you expect late events. It fits really well within the Databricks and Delta Lake ecosystems. Overall, it offers a simpler development complexity, often using static, predefined watermark intervals.
Got it. Next up, Apache Flink. How does that compare?
Flink is often positioned as the choice for true real-time processing. It handles data record by record as it arrives. No micro-batching in the same default way as Spark.
Ah, okay, so potentially lower latency.
Potentially, yes. It offers native event-time-based watermarking that is known for being incredibly flexible. You have a lot of control.
But there's a trade-off.
The trade-off mentioned is complexity. It's often listed as being more complex to implement and tune correctly. You might need custom code to get the watermarking just right.
What makes it so flexible, though?
A key feature is its strong support for fully dynamic watermark adjustments. The watermark can actually adapt based on the patterns of data arrival it's observing in the stream.
That sounds powerful.
It is. And it also has advanced back pressure handling, which is crucial when data is flowing in so fast it threatens to overwhelm the system. Flink can signal back to the source to slow down a bit.
So where would you use Flink then?
It's often recommended for really low latency use cases. Think Internet of Things, sensors needing immediate reaction, real-time fraud detection, high-frequency trading, those kinds of event-driven applications where dynamic watermarking is a big plus.
Okay, makes sense. Now what about Kafka streams?
Kafka Streams is interesting because it's tightly integrated with Apache Kafka, which is a hugely popular platform for handling data streams in the first place.
So if you're already all in on Kafka,
Then Kafka Streams might be a very natural fit. It processes event time data using timestamps embedded in the Kafka messages. And like Flink, it generally offers true, real-time, record-by-record processing.
implementation complexity.
It's considered moderate. You typically need to provide something called a timestamp extractor to tell it how to find the correct event time in your data. Its watermark adjustments are mostly static, like PySpark's default.
Specific.
Really ideal for building stream processing applications directly on top of Kafka, especially for pipelines with sort of moderate windowing requirements. It leverages that deep Kafka integration.
All right. And the last one in the comparison, Apache Beam.
Beam's big selling point is portability and flexibility, especially across different cloud environments or different processing engines.
Portability.
How so? Beam provides a unified API for defining your data pipelines, including native portable watermarking logic with good support for late data. The key is you can write your Beam pipeline once.
And then run it on different underlying engines.
Exactly. You could run the same Beam code on Apache Flink or Apache Spark or Google Cloud Dataflow, for instance. It offers that abstraction layer.
Processing model. Real time. Micro batch.
It can do both, effectively. It allows for micro-batching through things called window triggers, but generally offers near real-time processing capabilities. Complexity is seen as moderate.
And watermarking.
It supports dynamic watermark adjustments, adding to its flexibility.
So the best use case for Beam is?
It really shines in complex, perhaps multi-cloud scenarios where you need highly portable pipelines. Or if you need very flexible windowing strategies that you want to define independently of the execution engine.
Okay, wow. So 4 platforms, 4 different approaches, really. What does this all mean for you, the listener, trying to make sense of this?
It really boils down to your specific needs and priorities. Are you optimizing for ease of use and integration within a specific ecosystem like Databricks that might point towards PySpark?
Or do you need absolute rock-bottom latency and highly dynamic watermarks, even if it means more complex development?
Then Flink might be the answer. If you live and breathe Kafka, Kafka Streams is a strong contender.
And if you need that pipeline to run anywhere, across clouds or engines, Beam offers that portability.
Exactly. The choice depends heavily on those factors. Latency requirements, ease of use, existing ecosystem, multi-cloud strategy, and the complexity of your windowing logic.
Great comparison. Now, to really hammer these concepts home, let's get practical. Can we walk through one of these, maybe the PySpark example step by step, show how watermarking actually looks in code?
Absolutely. Let's ground this. Imagine again you're processing that stream of temperature readings from various IoT devices.
Okay, got the stream in mind. Each reading has an ID, a device ID, and crucially, that event time step.
Right. So step one, obviously, is setting up your code to read from that streaming data source, Kafka, Kinesis, wherever the data is coming from. You get your initial streaming data frame.
Standard stuff. Then comes the magic.
Then comes the core watermarking step. In PySpark, it's remarkably straightforward. You typically call a method on your streaming data frame something like streamingdf.withWatermark, event time, 5 minutes.
Just like that. And that tells PySpark.
It tells PySpark two things. First, which column holds the event time here, it's event time. Second, the threshold for lateness here, 5 minutes. It's basically saying, track the event time using this column and expect that events might arrive up to 5 minutes late relative to the latest event time seen so far.
Okay. And what happens based on that? What's the behavior?
This is crucial. Late events, meaning events whose event time is older than the current watermark but still within that 5-minute tolerance window, will still be processed and included in their correct time windows aggregation.
So it gives them a grace period.
Exactly. But, and this is the key part, if an event arrives beyond that 5-minute delay relative to the watermark's progress, it will be dropped.
Can you give an example?
Sure. Let's say an event actually occurred at 9.550000 a.m. If it arrives at the system and the system's watermark hasn't yet advanced past, say, 10:0000 a.m., that 9.55 event will be accepted and processed.
Okay.
But if that same 9.5500 a.m. event shows up much later, and by the time it arrives, the system's watermark has already moved forward to, say, 10.01.00 a.m.
Then it's too late.
Yeah.
More than 5 minutes past the 9.55 event time relative to the watermark's progress.
Correct. In that case, PySpark, following the policy set by withWatermark, will drop that event. It won't be included in any aggregation. This is that explicit policy ensuring the system doesn't wait indefinitely and can finalize results.
Right. That makes the trade-off very clear. Okay, so step 1, read the stream. Step 2, apply the watermark. What's next?
Step 3 is defining your aggregation using windowing. You've got your watermarked stream, now you tell PySpark what to calculate.
Like our average temperature example.
Precisely. The example code might look something like grouping by a time window based on the event time column, maybe 5-minute windows, and also grouping by the device side. Then calculating the average temperature within each window for each device.
Group by window. Event time, 5 minutes, cold device side, dotted G, AVG temperature, something like that.
Exactly like that. You define the window, the grouping keys, and the aggregation function.
Okay, and the final step. Where do these results go?
Step 4 is writing the aggregated results out, usually to what's called a sink. In the Databricks world, this is often a delta sink, which is a highly optimized table format built for this kind of thing, handling streaming updates reliably.
And there's something else critical in this step, isn't there? Something about checkpoints.
Ah, yes. Absolutely crucial. When you define your output stream writer, you must specify a checkpoint location.
Okay, let's pause here because this sounds important. Checkpointing. What is that actually doing and why is it so vital?
It's fundamental for making streaming applications robust and fault-tolerant. Think of the checkpoint location as a dedicated persistent storage place, usually on a distributed file system like DBFS, S3, HDFS, ADLS, something durable.
And what does Spark save there?
It saves all the critical state information about your running stream. This includes things like the exact position or offset it reached in the input data source.
It knows where it left off.
Exactly. It also saves the intermediate state for stateful operations like our windowed aggregations. It needs to remember the running counts or sums for windows that haven't closed yet.
Makes sense.
It also stores metadata about the progress of the stream, the current position of the watermark itself, and commit logs to ensure data is written to the output sink exactly once.
So this tackles the what if my job crashes?
Problem. Precisely. Checkpointing enables fault tolerance. If your streaming query fails for any reason, node failure, bug, whatever, you can restart it and it will read the last successful checkpoint.
And pick up exactly where it left off.
Right.
Without losing data or processing duplicates.
Correct. That's how it helps achieve those exactly once semantics we talked about earlier, ensuring every piece of input data affects the final output precisely one time. It's critical for data integrity.
So best practices around checkpointing.
Definitely use stable, durable storage, not just a local path on one machine. Never, ever manually delete or modify the files in the checkpoint directory unless you really know what you're doing and want to restart from scratch.
Right. Don't mess with it.
And give each distinct streaming query its own unique checkpoint directory. Don't share them. Also, ensure that checkpoint directory persists across application restarts or upgrades if you want seamless continuity.
Got it. Checkpointing equals robustness. And thinking back to PySpark's microbatching, is there any control over how often it processes those batches?
Yes, there is. When you start the stream writer, you can add a trigger. For example, you could specify trigger processing time 30 seconds to tell Spark to wake up and process whatever data has arrived in the last 30 seconds.
So you can tune the trade-off between latency and maybe efficiency.
Exactly. You control that micro batch interval. And one more cool thing, you can actually monitor the watermark's progress in the Spark UI.
Yeah, really, you can see it advancing.
Yeah, the UI often shows you the current event time watermark value, so you can see how far behind processing time it is or how it's behaving based on the data flow. It's a great way to get visibility into what's happening under the hood.
That's incredibly useful for debugging and understanding performance. Okay, this has been a fantastic deep dive. Let's try and summarize.
Sounds good.
We've plunged into the world of watermarking techniques. We've uncovered how they are absolutely essential for tackling that tricky problem of late arriving data in real-time streaming platforms.
Right. We saw why they're critical for getting accurate results from those window-based aggregations, counting things over time, averaging things over time.
And we compared the different philosophies and approaches of four major players: PySpark structured streaming, Apache Flink, Kafka Streams, and Apache Beam.
We saw that ultimately watermarking defines that threshold. It lets the system decide when it's seen enough to finalize calculations for a past time period, balancing that need for real-time accuracy against system performance and the reality that data doesn't always arrive on time.
And the choice between those technologies really depends on your specific context.
Absolutely. It aligns directly with your needs around latency, how easy you need it to be, integration with your existing tools, governance requirements, and, of course, how much data you need to scale to handle.
So hopefully, you now have a much clearer picture of how these critical data systems manage the inherent messiness of real-time information, ensuring they can still produce accurate results even when data arrives out of sequence or behind schedule.
It's a fascinating intersection of theory and very practical engineering.
It really is. And, reading through the source material, there's this Zen proverb included multiple times. To be calm is the highest achievement of the self.
Interesting connection.
It made me think. After wrestling with all this complexity, the late arrivals, the out-of-order chaos, the constant need for precision and fault tolerance is building these truly robust, reliable streaming systems that can intelligently manage all that chaos. Is that a kind of technological equivalent? Is it a form of achieving calm or mastery in this digital realm?
That's a really provocative thought. What would it mean for a complex data system designed to handle inherent unpredictability to achieve that kind of calm, that state of highest achievement? Something to definitely mull over.